Alright, so from yesterday,
Same thing.
had the cart, pulled the tape, and all this good stuff. So here's roughly what your two graphs should look like. Your velocity time graph's going to start at 0, because oddly enough the cart wasn't moving. And then it's going to speed up and then achieve somewhat a semblance of relative velocity. And then your position time graph's going to start at 0, 0, and then it's going to come up like this. Now, the whole key to this is that you have to realize that both graphs show the same thing happening at the same time. Now, the problem that you run into is a function of scale. Well, what were your velocities like? Maybe 3.5 centimeters per interval, something like that? Ballpark?
Like at which interval?
Just like when at 2. About 2?
Yeah.
Okay.
2.5.
So here's the deal. So I'm guessing this scale might have gone like 3, 2, 1, okay? So with this scale being so small from 1 to 2 to 3, if you have any variations at all, it looks like it's this huge thing. Oh, well, this isn't constant velocity, okay? Well, you're talking a difference in the intervals of maybe like, maybe 1 or 2/10 of a centimeter, okay, which is basically the thickness of your fingernail. So it looks like it's not constant velocity at all, but it's just because of the fact that your scale is set up where you can see these subtleties. Now, down here on your total position versus time graph, I'm guessing you ended up somewhere out here at about 20 centimeters. Okay, just a ballpark. Okay. Now, with this one, because the slope of this line shows velocity, because this scale goes all the way to 20, you can't pick out the real small subtle changes like you can on this velocity time graph because of the difference in the scale. Okay? So here's what you want to look at. And you have to understand how velocity is shown in both situations. So with this velocity time graph, okay, and keep this in mind, this velocity time graph can only show one of two things. You're either going to show constant velocity, and it's a horizontal line, or you show it speeding up or slowing down. Okay, that's it. Okay, those are the only two games in town. It's either constant velocity, speeding up, or slowing down. So if you look at this, going, well, we're starting off, we're speeding up, and then kind of on average, it kind of levels out. We kind of get this nice constant velocity. Now, and this is one of the key things when you get to number 5. This also shows the fact that this thing is speeding up, because at the bottom, remember this position time graph, the slope of this line shows velocity. So when you're starting off slowly, this thing has a more shallow slope. Then, as it speeds up, these lines become steeper and steeper and steeper until at some point, this becomes this relatively straight sloping line. So when this is a straight sloping line here, that correlates with this graph up here plateauing out. Okay? So both have to show the same thing. So when you have a curved line on a position time graph, that correlates with the sloping line on a velocity time graph. When this is a horizontal line here, this is a straight sloping line here. Okay, so that's one of the key things I want you to point out on question number 5. Okay? Now, at some point on your velocity time graph, you need to calculate that average velocity. Just take your overall total displacement at the end of that 10th interval, divided by the number of intervals which you have, which is conveniently 10. Okay? So like if your total displacement was 24 centimeters, you divide that by 10, you get 2.4. You're going to come up here and you're going to draw a line across here at 2.4. Saying on average, this is our velocity. Now, if you wanted to, and hopefully this would make sense, and this is where this goes full circle. If you take that average velocity line, okay, and you find the area underneath that curve, right, and this is what we talked about yesterday, the area bound by a line and the 0 meter per second line represents what? Displacement. So if you found this area for your average velocity, guess what? You're going to figure out how far it went. So, because it's just going to work in one kind of big vicious circle. Okay? Any questions? Going once? Going twice? So, all right, so here's what we got today. We're going to take this whole idea of velocity and what happens, how you describe motion, kind of like to the next level. Let's start with what we already know. So let's say after school today, you want to go to Kansas City, but you don't have time because you got a bunch of homework to do. So you call up Dad and say, hey, Dad, need to borrow the corporate jet, need to get up to Kansas City, need to hang out there for a little bit, then we're going to come right back. Dad says, sure. So you're going to fire up the corporate jet, fly from Wichita to Kansas City, and let's say it takes an hour to get up there. Okay? So it takes an hour to get to Kansas City. You're in Kansas City for an hour, and then you're going to come back to Wichita. Okay? So a total of 3 hours. An hour up, an hour there, an hour back. So I'm going to draw the position time graph for this trip. So what's the first thing that you have to establish? Reference point. What do you want the reference point to be? Wichita, Kansas City, Moscow? Wichita. Okay. So we're going to go from Wichita to Kansas City, stay in Kansas City, and then we're going to come back. So what's the position time graph going to look like?
Stay there for a little bit.
Kind of like a trapezoid?
Yeah. With some curve. Yeah.
Okay. So maybe a little bit of curve there at the bottom. Then something like this. So there's like 1 hour, and there's 2 hours, and there's 3 hours, right? So you're starting off slow. You know, the plane gets up to cruising altitude. We slow down a little bit before we land. Hopefully we slow down a lot. And then we're at rest in Kansas City, not moving. And then we turn around, we speed up, we cruise back down, we slow down a little bit before we land. Life is good. No worries. Okay? Now, and this would be at Kansas City, so this would be like 300 kilometers. Now, Dad says, hey, sorry, you know, the engine's been acting up. Can't borrow the corporate plane, but you can borrow the Corvette, okay? And you can drive to Kansas City. So if you were to drive to Kansas City, okay, so here's the deal. Now you're going to drive to Kansas City. You're still going to spend an hour in Kansas City, and then you're going to drive back. So what would happen to that graph? Would it still be the same kind of general shape? Yes. Why, Paige?
Because you're not really changing anything else. You're just changing like the time.
Okay. So what would happen to the slope of this line if I was driving to Kansas City?
And they keep going, like get longer. The lines will get longer.
Maybe more shallow? The slope wouldn't be as much?
Yes. No.
Yes, no? Let's say it took you 3 hours to get to Kansas City. So here's my 3 hour mark, right?
Okay, then yes, it would get more shallow.
Good with that?
Yes.
You sure?
I hope.
You hope?
We're the least
Yes.
confident class ever.
I think you're right. Okay?
I don't think so.
I think you're right, because at the 3 hour mark, I'm going to start at 0, and that's going to go something like this. True? Now, remember, the steepness of the line on a position time graph indicates what? Your velocity. So here's my line going from here to here. So my velocity isn't as fast, even as a Corvette, as it is compared to the corporate jet. So the line's going to become more shallow. I'm in Kansas City for an hour. Okay? So that gets me to my 4 hour mark. And then I'm going to turn around, I'm going to come back. So whether I'm flying or driving to Kansas City, it has the same general shape, right? The only thing is that it gets stretched out further. And if Dad says, well, hey, here's the deal with Corvettes even down, I got a horse you can ride. Okay. Well, You ride the horse all the way to Kansas City and you come back, you just stay for an hour. Why? You just stay for an hour if you drive the horse all the way to Kansas City. But even on horseback, okay, this thing would, right, get way shallow, okay, but it would still have the same general shape. Good so far. Now, I would argue that for the flight to Kansas City, the position time graph would actually look something like this. I think that's the position time graph for the Kansas City trip. Why? What'd you say, Cindy? What might that different reference point be? Oh, I'm flying to Kansas City, right? So Cindy says, whoa! And Logan's going, no, seriously. Okay? Look, if I were to... It's valid, though. Because look, visualize this. This graph, if you think about it, it's like you're looking down on top, right? And you're seeing the plane or the car start in Wichita, and you're going to see it leave Wichita, go to Kansas City, stay there, and then come back. So this graph has the exact same shape. This graph doesn't pick up the fact that the plane is actually flying up in the air, cruising at altitude, and then landing. Okay? The only thing this graph can keep track of is movement along the ground. Okay? That's it. Nothing else. So, and this is what you have to visualize. Even though we have for the plane, we have it going up, boom, coming back down, that doesn't mean, based upon this graph, that means the plane's actually going up in the air. All you could know is that you're here, you're going away, you're coming back. Think about the graph that you all did yesterday. For that lab that you all did yesterday, that position time graph started here, and then it sloped up like this. Now, does that mean that your little dozer started on the ground and then climbed up a mountain? No. It means it started at one point, you were in effect looking down, keeping track of the dozer going in one direction. Problem, Scraper?
I just spilled water.
I got a big roll of paper towels behind you.
That's okay.
Okay.
It wasn't that much.
All right, we're good?
Yeah.
Okay. All right. Now, so just because you see a position time graph sloping up, that doesn't mean that it's going up in the air. Now, what Sydney picked up on is very keen observation. Because of the fact that this thing is going to be flying, so in other words, we're going to keep track, instead of horizontal position versus time, we're going to keep track of vertical position versus time. So basically, what we're doing with that graph is we're making the ground the reference point. So we're saying the plane starts here, it goes away from the reference point, cruises at altitude, comes back down, is on the tarmac for an hour, and then leaves the ground, and then comes back down. Now, with this graph, keeping in mind that we are in Kansas, if you were to drive, would this graph look completely different? Yes, what would it do?
Those straight lines.
Yeah, it would make, we're in Kansas. So basically, you're going to drive along, oh, hit the Flint Hills, okay, right? You're in Kansas City, hit the Flint Hills again, okay? That's about it, okay? So in Kansas, this would basically be a flat line. And somebody who was really bored actually did a study and compared like the surface of Kansas to a pancake, and on the same scale, Kansas is actually flatter than a pancake. Okay, they were really bored, but yeah, Kansas is actually flatter than a pancake if you could put it on the same scale. Okay, so one of the things that you have to keep track of when you're looking at position time graphs is which axis are you looking at? Are you keeping track of vertical versus time, or are you keeping track of horizontal versus time? Now, what's true no matter what you do, no matter what, if your slope changes sign, you did what? You changed direction. So this one, you climbed up to altitude, you cruised like that, and then you landed. Stayed there, cruised to altitude, okay, came back down. So no matter what, every time that you change, the slope changes sign, that means that you change direction. Okay? Now, shut that down. We need to go back to our schedule. Yeah? Okay. All right. Are we ready?
Yep.
All right. So here's what we've got. So we're going to look at this section of this roller coaster from here to here. Now, for those of you that have ridden on roller coasters, what provides the thrill of a roller coaster? Constant velocity or accelerated motion? Yeah, constant velocity roller coasters are boring. Okay? Ooh, I get in a line, I get on it, I move in a straight line at a constant speed. Ooh, big thrill. Now, if the constant speed happens to be like, faster than the speed of sound, okay, legitimate, that would be cool. But for the most part, constant velocity roller coasters are not going to sell very well. Boring, okay? So the whole thrill of roller coasters, if you think about it, comes from changing either the direction of your velocity vector or the magnitude of your velocity vector. Okay? That provides the thrill. Okay? You're either going to speed up, slow down, or turn. So, what we're going to look at is what's going to happen between this point on the roller coaster and this point over here. Okay? So, we're going to start up here. Okay? I want to do it again. Guys, you ready?
Yeah, ready.
Okay. What is the difference here? Oh, come on. Oh, crash and burn. Okay. Somebody's going to get sued. All right. So, we're going to look at this thing from this point to this point, and we're going to draw the position time graph. So, what's the first thing that we have to establish? Sydney?
Direction.
Kinda, right? So think about what we just did up there with the plane flying, right? So what's the
Reference
first?
point.
Well, okay. What do we want the reference point to be?
Starting position.
Which one?
That one.
This one?
The top of the hill thing.
Top of the hill.
Yeah.
Yeah.
Now, are you going to keep track of horizontal position versus time, or vertical position versus time?
Vertical.
Let's do vertical. So do you want to start there?
I lied.
Oh, let's
Start the table.
You want to make the table the reference point
Yeah.
because you're going to keep track of vertical position versus time.
Yes.
Okay, so we're going to make this the reference point. We're going to start up here, right? Then what's it going to do?
Start up high and level off, and it's going to slowly go down.
And then what?
But then it's going to get high again.
It's
and
gonna
go
go
back
low.
down.
Then it's going to get high again, otherwise known as the Colorado curve. Okay?
It's gonna
And then it's going to
level out again.
level back out again, and then it's going to
Come back up.
go back up. So you're saying, if I may, so here's vertical position versus time. So you're saying it's going to start up here and then do what?
Go down.
Go down?
Go up.
Go back up?
Down.
Go back down?
And then a little.
Then up a little. Something like this?
That's perfect.
Now, but that doesn't include the loop. That roller coaster clearly had a loop.
It can't go back in time.
You need to put one more hill on it, and then we'll include the loop.
Wait, what?
Because it starts up high, and it goes back down, and it goes back up on the loop. It goes back down, and it goes back up here.
Yeah.
So it needs to go up one more time. Liar.
You
You
are a
just don't
liar.
understand what I'm saying.
It can't go back in time.
Okay. Oh, let's, could we, what would happen if we didn't? But what would happen if we did this? Why not?
Because it's time, you can't go back.
Yeah, we can't go back in time, okay? Now, which would be cool, okay? Now, could we look at this from a function standpoint? So for those of you that are math nerds, if something's a function equation for each value of x, how many possible values of y can there be? One. So if you do like the vertical line test, okay, and let's say you did have this line where it went like this, and you drew a line like this, that means that this, physically, if you drew this line, you can say, at this point in time, you're where?
Two places at once.
Yeah, you're at both places at the same time, which would be cool, okay, but not probably going to happen. So that's the advantage, right, of doing this, because we can't even really have like a vertical line, because a vertical line would mean that we're at all these positions at the same time, which would be kind of cool, but really not going to happen. Now, so if all I gave you was this graph, okay? Read, if all I gave you was this graph, Mr. Green Lantern, okay? If all I gave you was this graph and asked you how many times did that thing change direction, what would you say?
Twice, maybe? 3 times?
Twice maybe? 3? Do I hear 4?
Sure.
No, don't. No, don't. You don't hear 4. Why 3?
Because there's 3 curves.
Okay? Now, what are the 3 things that have to happen to change direction? You have to
Stop.
speed back up. So, at this point, okay, right here, at this bottom, am I slowing down? Because the slope is becoming shallow. Now, at the very bottom, okay, we'll talk about tangent lines here in just a second. If I draw a tangent line here, tangent lines on position time graphs gives you instantaneous velocity. So at the bottom, I have an instantaneous velocity of 0. Then, what do I begin to do? Speed up. Now, what's the sign of this line coming down like this, positive or negative? Negative. Here I have, so I'm going from negative slope to positive slope. The slope changes sign, therefore I change direction. Now, what happens up here? Same thing. I go from positive slope to negative slope, and at the top my velocity is 0 because I am
Stopping.
to change direction. Down here, same thing. So basically, if you want to think about this in terms of you that are math nerds, every time you have a relative maximum or minimum, that's when you're going to change direction. Okay? It's the only time you really apply something that you really learn in math class outside of this. So, relative max, relative min, we're going to change direction. Now, here's the question. Could I generate this exact same curve without a loop?
Yes.
Danny, what could I do? How could I generate that curve without a loop?
You could just have like another hill instead of a loop.
Beautiful. Okay? If I just had this thing coming down, going into a loop, coming down, and then coming back up over here, I would generate the exact same shape without the loop. So, if all you saw is that, you could not figure out that this thing has a loop. The only thing you knew is that this thing started high, goes down, goes back up, goes back down, comes back up. That graph alone will not tell you that there's a loop. Now, let's talk horizontal position versus time. Okay? So if I'm going to do horizontal position versus time, right? So, what's that going to look like? What's the first thing you have to establish? Where do you want the reference point to be? Here? Okay, so we're going to make this the reference point. So Elijah, at the beginning, this is the reference point. So what's my position time graph going to do?
Okay, it's horizontal, right?
This is, yeah, we're going to keep track of horizontal position versus time. So imagine that you are up here in a balloon and you're looking down. And the only thing you can see is horizontal position, and that's the only thing you can see. You can't see if it's going up or if it's going down. So it's going to start here, and then what are you going to see? You're going to see it go away, then what?
Come back.
Then you'll see it come back, and then you're going to see it go straight again, right? So you see it start here, go forward, change direction and come back, and then change direction again and go forward. So, Elijah, here's what I want. How can I show this thing starting at the reference point? So this is going to be horizontal position versus time. Where am I going to start? At 0, 0, or am I going to start up here again?
0, 0.
Or start at 0, 0. So how can I show this thing going away from the reference point?
Constant.
Okay? That's probably going to speed up a little bit. Okay? Then what? I need to show a change in direction. How can I show a change in direction over here?
Change sign.
Change sign. So what can I do to change sign?
Back down.
I can come back down. Now, am I going to go all the way back to 0? No, why not? Why don't I go all the way back to 0?
Not coming all the way back to the
Yeah, I don't go all the way back to the reference point, right? The loop isn't that big. So I'm just going to come back a little ways, then what am I going to do? Now I'm going to start to go away again, so what am I going to do?
Go back.
Something like this?
Yeah.
Beautiful? Fantastic. Okay. Mr. Baker, based upon this graph, how many direction changes do I have?
2.
Why?
Because the graph only changes directions twice.
Yeah, here and here. So I have 2 direction changes. So the velocity went to 0 twice. Now, could I generate this curve without a loop?
No.
Really?
What if you have
Maybe.
multiple things?
Yeah, you could go like this and then do a little swivel back and then go forward.
Do a little swivel back.
Like if you would turn backwards and then go forward.
Like an S curve.
Yeah.
So you're saying that I could have it come down, just make a big general curve, and then go out like
As
this,
long as it's going back towards reference.
as long as it's going back towards the reference point. What else could I do?
Make it back up.
There are more than
What if I had just a big horizontal loop?
Yeah.
Okay? In other words, if I, instead of having a vertical loop, if I came out and just had it go around like this, would that do the same thing?
Yes.
Yes. So, one graph by itself will not indicate that you have a loop. But if you put both of them together and go, wow, I'm getting a going up and coming back down, okay, vertically, and at the same time I have a horizontal change in position. So like if you superimpose the 2 graphs, the only way that can happen is if you have a loop, where you have a vertical change at the same time that you're having a horizontal change. Got it? Good? Okay. Let's say, hypothetically, that I gave you that straight sloping line that starts at 0, 0, and ends up at 8 meters and 4 seconds. Read. What? That's a simple question.
Come on.
How could you find the slope of that line?
Yes.
What would the slope of that line be?
2.
2 what?
2 meters per second.
2 meters per second. Because if you take 8 minus 0 and divide that by 4 minus 0, you're going to get 2 meters per second. Now, read. What's the velocity at 2 seconds? Don't make this difficult.
2 meters per second.
2 meters per second. Does it make any difference which point in time I pick?
No.
Why?
Because it's a constant slope.
Yeah, so it has constant velocity. So no matter which point I pick, as long as it's a straight sloping line, I could pick 2.13724 seconds. No matter what point I pick. I can pick pi seconds. Doesn't make any difference. No matter which point I pick, every point on that line is going to have the exact same slope. Right? So, doesn't make any difference. Now, here's the problem. What if we change this into something like this, and I said, okay, now I want to know what the velocity is at the 2-second mark. What could you do?
Figure out the slope of that line from the beginning point to the 2-second point.
But the slope's always changing.
It's true, so.
Find instantaneous
Just
velocity.
not worry about it.
Derivative.
Just not worry about it, skip that and move on.
Skip that problem.
I'll concede that one. Hopefully I'll get the rest of them right on the test. No. Okay. Now, pretend that you all are back in geometry. And I draw a circle, and I draw a radius to that circle, and I say, I want you all to draw a tangent line to the circle.
Yes. Yes.
Yes. It really wasn't a yes-no question, but yes, you can, or yes, what?
We can.
Yeah.
Yes, you can. Now, what do you know about tangent lines to circle?
Only took one.
Elijah, it only touches at one point, right? Which means that it has to be at a right angle
Right angle.
to the
Radius.
radius. So if I were to come in here and draw a line like this, so this would form a right angle to that radius, and it would only touch the circle at one point. Because if I try to draw my tangent line like that, what's wrong? Yeah, it goes through two different points. Bad. Okay? So we'll make that one go away. Now, if I drew the tangent line like this, okay, or if I drew my radius line like this, then the tangent would go something like this. Okay? So you can draw tangent lines all the way around as long as they only touch the curve at one point. And it's at right, and it's always going to be at right angles to the radius. So, if I go to this 2-second mark, now this is where there's two ways you can actually find this instantaneous velocity. If you know the equation that actually generates the curve, and you've done calculus, you can take the derivative of the line and then generate the slope of the curve at that point. Okay?
Yep.
You there?
I know. Yeah, I got
Yeah.
it. That's what we did. That's what we did yesterday. So.
Ironically.
Yeah.
Now, since we don't actually know this, right? So what we're going to do is we're going to do a graphical method. So this takes a little bit of creativity and a little bit of vision. So what you're going to do is imagine, if you will, let my line change color. There we go. So imagine, if you will, that this is part of like a larger circle. So when you want to find instantaneous velocity, I will give you a specific time. I'm going to say I want to know what the instantaneous velocity is at exactly 2 seconds. Okay? So you are going to be given a specific time. So if you imagine this being part of a circle and the radius of the line being something like this. Some people actually draw in the radius, okay, to get a visual. So you're going to come in here and you're going to take a straight edge, okay? This has to be done with a straight edge. You cannot freehand this, okay? This has to be done with a straight edge. So you're going to come in here and say, okay, I want the 2-second mark. So I'm going to tell you, I want the instantaneous velocity at the 2-second mark. So you're going to come up here at 2 seconds and you're going to find where it hits the line. Then you're going to draw a line that touches just at that one point. Okay? So something like this. So this would represent my tangent line. Now, let's say that point right there, just to make up some numbers, let's say that point is 2 meters, or excuse me, 2 seconds and 2 meters. Okay, so that's that point. Now, listen to me. Listen to me. Here's what you cannot do. Even though it goes through the point 2 meters and 2 seconds, you cannot say, oh, that's the slope of my line. I'm just going to take 2 meters and divide it by 2 seconds and go, oh, that's the slope of my line, 1 meter per second. Why can't you do that?
Because you have to know your radius.
Nah, not really.
It's not a straight line.
Yeah, it is. It's a straight line right there.
That one right there, because it's not
Because it doesn't go.
Sure it is. It's part of the graph. It goes through that point 2 meters, 2 seconds.
There's the y, the y-axis. It doesn't go through the origin.
What'd you say, Riley?
Gotta have 2 points to find the slope.
Bingo! You have to have 2 points to figure out the slope of line. Because if you just take this point 2 meters and 2 seconds and say, oh, it's 1 meter per second, then you're going to say no matter what line I draw through that point, it's all going to have the exact same slope. Remember, you have to have 2 points, Euclidean or non-Euclidean geometry, to define the slope of a line. So, you can use that as one of your points. Okay, it's very valid. You can use that as one of your points. But you can't just say, oh, I'm just going to take the 2 meters and divide it by 2 seconds and go, my slope of the line is 1 meter per second. Won't work, okay, in any way, shape, or form. So, what you could do is you could come out here and say, well, this is 4 seconds and that's like maybe 8 meters. So you could come out here and say, okay, well, this point out here is 4 seconds and 8 meters, okay? So that could be a set of points that's on the line. These have to be points that are on the straight line that you drew, not points that are on the curve. Now, they might happen to match up, but the points that you pick to find this instantaneous velocity are on the tangent line, not on the curve. So you're going to eyeball it, draw it. Now, I know there's going to be some variation because, you know, there's going to be some variation in the slope of this. It's not going to be exact. That's the beauty of doing calculus, is if we would have an exact answer, because we know the equation that generated the line. So, I can find the slope of this line, just like you all have done hundreds of times before. I would take, in this case, 8 meters minus 2 meters, and divide that by 4 seconds minus 2 seconds, and I would get 6 over 2, and I would get 3 meters per second. So what I'm saying is that based upon the slope of this tangent line, at the 2 second mark, this thing has a velocity of 3 meters per second. Now, what if I said, I want to figure the velocity at this point, okay? Say the 3 second mark. Now, let's just visually look at this, okay? Just visually. If I were to come in here and draw it at the 3 second mark, visually, what can you tell about the slope of the line? Is it more steep or less steep, Green Lantern?
It's less steep.
So at the 3 second mark, my velocity should be less than it is at the 2 second mark. Okay? Now, Graver, if I were to go to the very top of this peak and draw a tangent line, what do you think the slope of that line is going to be? 0, which means that the object has an instantaneous velocity of 0, right? So at the very top of the peak, this is the relative maximum, the slope of the tangent line is going to be 0. Because again, there's 3 things that have to happen to change direction. You have to slow down, and that's what we're doing because our tangent lines are becoming more shallow. We have to, what's the second thing, Graver? Stop, and that's when that tangent line flattens out. And then, Elijah, what do I need to do? Speed up. And that's what's going to happen here. Now, look what happens. If I come over here and start drawing tangent lines, okay, right away, I've got positive slope tangent lines up to this point. Once I go over the top, then I have negative slope tangent lines, which means that I changes directions. See how it all fits together. Okay. Now, let's go back to a position time graph. And let's say that, I like this function. We have a line like this. Danny. This is a position time graph, okay? Could I draw tangent lines to that line? No. Why?
Because it's already a straight line.
Yeah, it's already a straight line. The only time you draw tangent lines is when you have curves. And curves on position time graphs indicate that the velocity is changing. Because that means if the velocity is changing, that means we're trying to figure out what the velocity is at a particular point in time. So another way to look at this, imagine that you're recording, don't do this, but imagine that you're recording the speedometer in your car. Okay, so you got your phone and you're recording this image. And it's got a timer, okay? So one thing you could do is if you just had that image, you could say, hey, I want to know how fast I was going 5 seconds into my drive. Go to the 5-second mark, look at how fast your speedometer is going. Okay? Go to the 7th second. Okay? So your phone would record how fast you're going at particular points in time. Okay? Good? But we don't have that. We can't do that. We're not recording how fast something is going as a function of time. So when you have a curve or something like this, the only way that we can figure out how fast it's going at a particular instant is to draw those tangent lines. And when you draw those tangent lines, that's what you're going to use to find the slope at that instant in time. So listen to me. Listen to me. The only time you draw tangent lines is under two conditions. Number one, when you're asked to find an instantaneous velocity and when the velocity is continuously changing. Because if it's a straight sloping line, it doesn't do any good. You just find the slope of the line. So you only draw tangent lines under very specific instances. So you use tangent lines give you instantaneous velocity, and you only draw those when you are accelerating. Or when you have curved lines on a position time graph. Okay? So, tangent lines get you two things. An instantaneous velocity, but you only draw that when you are accelerated. If you're moving at a constant velocity, there's no need for them because you can't draw tangent lines anyway. Got it? Good? Fantastic. Good. So shut that down. So with this, positions along the roller coaster. So let me kind of take you through what you're going to need to do. So you've got up at the top, you have a data table that says, okay, here's the values of time. Then here's horizontal position versus time. Here's vertical position time. So you're going to end up drawing three different graphs. If you're going to take a sheet of graph paper and divide it into thirds and do one on each, a third and a third and a third, that's fine. If you want to do halvesies, go half, a half, and then another half, that's fine. If you really like to kill trees and you want to put one on each page, hey, knock yourselves out. But I don't know how, I don't know how you're going to sleep at night, but that's up to you. All right, so on question number one, it says, using the graph paper, plot a position time graph for movement along the ground. So the first one you're going to do is that you're going to keep track of where this thing is horizontally as a function of time. So you're going to set up a scale, time along here, and you're going to have position here, but this is going to be horizontal position, okay, versus time. So it's like you're looking down on the ground. So this graph, okay, is going to be like the one you did yesterday with the constant velocity device. In other words, we're looking down, and the only thing we can keep track of is what's going to be happening along the ground. This is not vertical versus time. So when you look at that column, horizontal position versus time, are you going to start at 0, 0? Yes, because at 1 second you're basically at the reference point. Okay? Now, to give you, not to give it away, but this is what your graph is going to look like. When you get done, this horizontal position time is going to look something like this. Okay? That's what it's going to look like when you get done. Now, on question number 2, it says, is the velocity constant in the horizontal direction? Overall, for this trip, is it constant? Justify your answer. Now, on problem number 1, it says, describe the shape of the curve. You don't have, this is not your doctoral thesis, okay? Just say, what roughly does it look like? Okay? It looks like a snake. You know, what does it look like? Now, the whole key to this is question number 3. Listen to me what I want done on question number 3 at the bottom. At the 8 and the 12 second marks, draw the tangent lines to the curve and determine the velocity at these points. So, you're going to come here at the 8 second mark. Okay? So, you're going to pick the 8 second mark. And I'm going to tell you exactly the 8 second mark. Then, you're going to take your straight edge. And by the way, if you don't have your straight edge ruler, you need to have that by the end of the week. Or, excuse me, the protractor and straight edge. You have to have that by the end of the week. So, you're going to kind of eyeball this and go, okay, well, there's my curve. So my tangent line, is going to go something like this. So you are going to physically draw that line. Physically draw that line. And it's going to hit at the 8 second mark. Now, like I said, everybody's is going to be a little bit different. Then you're going to pick 2 points to find the slope of this line. So ideally what I would see is you say, okay, I'm going to pick this point and I'm going to pick this point. Okay? So I can see which points you pick. Now, either on the graph itself or in this space, I want to see how you found the slope of that line. I want to see black, 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 minus this, black minus that, whatever. Okay? I want to see how you found the slope of that line. Do not leave this line, the slope of this line, as a fraction. I want to know, hey, I'm going da-da-da-da-da meters per second. Okay? So, then you're going to do the exact same thing at the 12 second mark. You're going to draw that tangent line. You're going to pick 2 points. I'm going to know exactly which points you picked. There you go. Okay, so you're going to do that twice. You're going to draw those lines. You're going to find the slopes. Life is going to be grand. And I'm going to know exactly what you did. Because everybody's points are going to be different. Because everybody's tangent lines are going to be a little bit different. That's why it's so important that I know exactly what you did. Especially on this graph, if there's a graph that maybe you draw a little bit bigger, spread this out, do this one because you have to have the exact points on these lines to find the slope. Now, over on the back side, on number 4, at the 9 and 13 second marks, draw the tangents to the curve. Now, on these, if you draw them correctly, you can clearly see what the slope is. You don't actually have to calculate the slope. Because if you draw them correctly, you could look and go, oh, well, the slope is that. Okay, whatever it is. But the most important thing, and in big bold letters I typed, why is the velocity what it is? Okay? Why is that velocity that particular value? Then on question number 5, if you were in a balloon above the roller coaster, keep in mind you are looking down on top. The only thing you can see is horizontal motion. Based upon this graph, what would you see? Now, question number 6. Now you're going to plot position versus time for the vertical movement. So you're going to go back, you're going to set up the exact same time scale that you used as the first one, and now you're going to draw vertical position versus time. This one is not going to start at 0, 0 because the roller coaster is already up at its highest point. So the second graph, do not start at 0, 0. Now, on this particular one, you don't have to draw any tangent lines, okay? But you do kind of have to figure out what it's showing. Now, on question number 9, listen to me on question number 9, okay? You're going to draw the third graph. The third graph does not involve time, okay? It does not involve time. What are you going to do on this third graph? So, here's your graph paper. Okay? You're going to plot horizontal position, oddly enough, along the x-axis. Vertical position, oddly enough, on the y-axis. This does not have to be this way on the first two graphs, but it has to be on this third graph. You're going to set up a scale, and I don't care what the scale is. Maybe you're going to let each box represent 2 meters going this way. That's fine, whatever it is. But whatever the scale that you choose going this way has to be the exact same scale going up this way. So if you're going to let this be 2 meters going across like this, you have to let this be 2 meters going up. If you're going to let this be 5 meters going across, fine. But then you have to make this be 5 meters going up. So I don't care what the scale is, and I tell you this in the instructions, but you all are horrible at listening and reading instructions. So I don't care how you set up the scale. It just has to be the same. Because if you don't, then you get like roller coasters that look like this, or you get roller coasters that look like this. Okay? If the scales aren't the same. That's the importance of this. Now, when you get to question number 11, okay? Now that you know the shape of the roller coaster, what was happening between 7 and 15 seconds, between 17 and 24? So I'm basically asking you 2 different time intervals. What's happening between 7 and 15, between 17 and 24? Listen to me. Listen to me. At the end of this, I typed, reference both position time graphs in justifying your answer. So in other words, if you think between 7 and 15 seconds, you think this thing is just going down a hill. And that's all. You just think it's going down a hill. Fine. How do you know that it's just going down the hill based upon the horizontal versus time and the vertical versus time? So you would say, I think it's going down the hill horizontally because this graph is doing this. And vertically it's doing this. Okay? Now, between 17 and 24, you think it's going up a hill. Well, how do you know that it's going up a hill based upon both graphs? So listen to me. You have to reference both graphs. So you're going to say between 17 and 24 seconds, I think it's doing this. Why? Between 17 and 24, whatever, you have 2 different times. On both of them, you reference both graphs. Okay? And be very specific in that explanation. Okay? Beautiful. All right, I'm done. You're on your own. If you need some graph paper, there's some back there.